Hello everyone, welcome to our next lecture in the series Competition Policy and Strategy. Today we're talking about two-sided markets. It fits nicely into our schedule as in chapter H we have first been talking about collusion, so basically all sorts of illegal cooperation between firms. Then we have been talking about horizontal and vertical cooperations, which are not illegal, basically. And in chapter H3, we have been talking about vertical restraints. So basically, all sorts of things along the value chain that impede or supposedly impede competition. And now we're taking a step further to look at a hybrid form between this upstream-downstream problematic. So it's quite related, but it's also different. Before we start, please make sure to like the video, subscribe to our channel, and if you have questions, please leave them in the comment section below. Let's get started. Oh, that's not so smart. Let's do it that way. So, what is a two-sided market? In order to understand what a two-sided market is, it makes first of all sense to talk about one-sided market. A one-sided market is something that we have been analyzing throughout the course when we have been talking about upstream and downstream firms. So it was basically a situation where we had a retailer of a product that was produced by an upstream firm, right? So an upstream firm produces a t-shirt, it delivers the t-shirt to a retailer, and the retailer sells the t-shirt to the consumer. That would be a one-sided market. Now, if we have a two-sided market, then we're talking about something that we also call platform markets. And the idea of a platform is that it matches buyers and sellers. And the crucial point here from an economics perspective is that the platform internalizes indirect network effects and externalities. And that's what we're going to talk about today in a lot of detail. What are indirect network effects? So it's basically a type of externality in a sense that if the other market side becomes bigger, larger, more if there are more people on the other market side, then the utility of a given market size increases. So what does this mean? If you have a platform that matches buyers and sellers, then buyers profit from more sellers on the other market side and vice versa. How can we get a hold of this concept? Well, look at a credit card, for instance. If you can pay with your credit card in more stores, then the credit card becomes more attractive for you as a, you could say, buyer of the credit card. Sorry, the buyer at this store, basically. And the more consumers use the credit card, the more attractive the credit card becomes, or the more attractive it becomes for the sellers to accept the given credit card, right? Another example would be operating systems or gaming consoles, for instance. So if you have, let's say, an Xbox, then it becomes more attractive for developers to develop games for the Xbox if there are more players that use the Xbox. And if there are more games available on a given gaming console, then it makes a lot of sense for the buyer, for the users to also use that platform, right? And the same applies to operating systems. If you have an operating system that only supports a few apps, then it's not very attractive for you, right? So that's the concept of indirect network effects, basically. So the console, or the platform, so the console in our example and the platform in general, benefits from more buyers and more sellers, basically. Okay, now, what is the function of the platform, basically? So the platform has to set prices for each market side, and it has to induce participation, basically. And if we talk about competition between platforms, then it gets crucial to talk about single and multi-homing. Single homing means that you only have one platform. What does this mean? Well, it would mean that users generally only use the Xbox or use Windows operating systems or use only one credit card. Whereas multi-homing would mean that consumers use the Xbox and the PlayStation and, for instance, a PC at the same time, right? Or if you talk about eBay, would also be an example of a platform. And if you can easily go to another auction platform, then you basically are able to multi-home. And the problem is that due to these, let's say, caveats, it is very difficult to apply our traditional concept of competition policy that we have learned throughout this course. In order to illustrate this entire concept, we're going to use the model that is established in the textbook of Belleflamme and Peitz. Keep in mind that we're going to keep the model or the exposition short here. So I'm going to give you I hope that I will give you a proper insight for you to understand the concepts, but if you want to derive the exact equations, I'm not going to do that here in detail. You could have a look at the textbook, or if you apply for the VIP program at JLU, you could, for instance, enjoy an exercise class, an online exercise class, where you get taught the where you get into more detail about the respective models here with illustrative examples, for instance. Okay, so how does the model look like? We have two market sides, B and S, and we could talk, we define them as buyers and sellers, because it's quite illustrative. Then we have two platforms two platforms 1 and 2, and the index I refers to these platforms. Then we have a per unit price, which is basically a usage fee. For instance, if you buy a game for a console, then this would probably basically be a usage fee. Or if you if you're on eBay and there's a per transaction fee that you're paying, then this would be a usage fee. And of course, you can set usage fees for each market size. And the same applies to a fixed fee or membership fee. That's something that means that you have to buy the gaming console, or you have to pay in order to have an account at eBay. That's probably something that for you as a buyer doesn't really matter, but for sellers it could, for instance, depending on the platform you're using. And these are the two prices here. So we have a variable fee basically and a fixed fee. And in order to get started, we just look at a situation where we have one monopolistic platform, so we don't look at, so the index I would be irrelevant, and we don't have platform competition, which makes the exposition and live a little bit easier here. So what does the platform do? It basically matches buyers and sellers, and in order to get an understanding, we basically assume that each buyer has a demand function which is falling, and sellers have constant marginal costs. So we don't get into much detail about that here because it doesn't really matter that much to illustrate the concepts. So based on these demand function and based on this demand and cost, we can assume that a seller charges a monopoly price which maximizes its operating profits here, and we get a surplus, a monopoly surplus here for each seller, and based on the monopoly price PM, we have for each buyer a utility or a surplus of U, right? So these two things here are endogenously determined if you have information about your demand and marginal cost, basically. We're going to treat this U and pi as given, right? So that is basically the surplus that, if you talk about pi, for instance, that's the surplus that one seller can generate by entering the platform, or if you talk about U, that's the surplus that one buyer realizes if he's on the platform. Now, based on this, we can think more about the joint surplus that we have on the platform. And that joint surplus is, from the viewpoint of the seller, we define that as VS, and that's If you are on the platform as a seller and there are small nb buyers, then for each transaction with a buyer you can realize you can make basically, you realize your operative monopoly profits pi, but you have to pay an access fee ms in order to access the platform. So what does this mean? Suppose your monopoly profit would be 10, so you earn 10 monetary units for each sale you make on the platform. And suppose you have 2 buyers, right? So you access the platform, you sell 2 units, and for each unit you earn 10, so your surplus would be 20. However, you have to pay an access fee in order to be on the platform, and that would, for instance, be 5. Right? And then we would have an operative profit of 20 and your fixed fee would be 5, so you have a surplus of 15 in our example. Right? And you could make up a similar example from the viewpoint of the buyer. So you know that each buyer realizes for each seller that is on the market, or for each sale, for each purchase that he makes, he earns his utility U, but he has to pay an access fee MB in order to access the platform. Now, it's something that's a little bit abstract, so at that point I would advise you to look at the textbook. There is the number of buyers, and that number is a function of your utility, right? So the higher your utility you get on the platform, basically the more buyers will be there. However, we have to, or in theory, we would also limit this, because there's also only a limited amount of buyers and sellers as well. So at that point, just realize that the number of buyers on the platform is a function of the utility that each buyer can realize by being on the platform. And the same applies for the sellers. Now, a platform, if it serves a buyer, and it occurs constant marginal cost CB, and the same for the seller. What does this mean? We learn from this that the platform profits capital pi are the number of sellers, or the number of transactions, or the number of sales a seller makes, is the access fee, or it's definitely the number of sellers. So the number of sellers that are on the platform, you get as a profit your fixed fee MS, or as a revenue you get your fixed fee MS, and you pay your cost that each seller basically generates, right? And the same applies to the buyer. So, for instance, if there are 100 buyers on the platform, and each buyer pays a fixed fee of 10, but costs you 1 unit, you have 100 times 9 as the profit that is generated from the buyers, right? Now, we can compute the fixed fees. How can we get up with this? How can we derive this expression here? Pretty simple. We have this here and this here. So this is the surplus that is realized by the sellers and by the buyers, and we see that this is a function of MS and MB, and we can just rearrange these two expressions here to get to here, right? So before we had VB is equal to NSU minus MB, and we just rearrange this, right? But we take into account that capital NS as a function of Vs is equal to NS, and capital NB as a function of VB is small nb, right? So that's what we had before. So we just substitute this and rearrange the equation that we had before. Now from this, right, so we have MS here, MB here, and we have rearranged and inserted here. So we now have an expression of MB and MS that we can substitute here and here, and then we get to this expression here, right? And this is our profit function. And what we now do is basically to maximize this profit function, and our instruments are the utilities that we leave to the respective parties, VS and VB. Right? So it's a little bit abstract, but it's relatively easy to come up with a solution at that point. Now, what you do in order to get your profit maximizing fixed fees, which are basically what we're interested in, all you have to do is to differentiate this function with respect to VS and VB, right? And how do we do that? Well, let's take VS as an example. So we differentiate our our platform profits with respect to Vs. Now we have Vs here, so we have minus capital NS, which is the same as small ns, by the way. And then we have Vs here as the argument of Ns, of capital Ns. So what we have is plus Ns, the derivative of Ns with respect to Vs times the expression in parentheses here, which is NB pi minus Vs minus Cs. And then in this expression here in the parentheses, we also have our Vs as the variable of Ns here. And now if we differentiate this one, we get to Ns, the derivative of Ns times U times NB, right? And that's our first order condition if we set this equal to 0, right? Now what you do in order to get to the profit maximizing fixed fee is to realize that this part here is exactly this one, right? So NB times pi minus Vs, that's exactly this. So this is exactly equal to Ms. Now we have this equation, we have Ms here, so all we have to do is to come up with is to rearrange this one with respect to Ms. What we do to get there is to just divide everything by Ns prime, noting that this is not 0. Then we get to here, and this cancels out. It's quite elegant. Sorry, that was, what was it? I think it was a U. Right, so this is the part that we have here, and now we immediately see that we're almost done. Basically, we just have to note that capital NB is equal to small nb, and then you see that we bring an s to the other side here. Then we have the plus ns over the derivative of ns term on the right hand side. We bring the cost to the other side, so we have cs, and we subtract u times nb, and then we are here, right? So this is what determines our profit maximizing fixed fee for the seller, and we can do the same for the buyer, right? So it's the same principle. Okay, so now we've arrived at the fixed fee of the seller, and we see that the fixed fee, or also the fixed fee of the buyer, we see that the fixed fees consist of the excess fees, the cost of excess CK and CS and CB. So how much does it cost if there is a buyer and a seller on the platform? And of course this increases the fixed fee. Then we have to take into account the second term here, so this one, and that is crucial, right? Because this is basically what drives the entire result. These are the network externalities, the network effects that play a role here. Because every seller, if he's on the platform, will attract some sort of buyer, or to some degree it will attract buyers, right? So if you increase the fixed fee for the sellers, you basically make it less attractive for the buyer to be on the platform. If you increase the fixed fee for the seller, you make it less attractive for the seller to be on the platform, and that has a feedback on the number of buyers. So it will reduce the revenues that you get, or the profits that you get from as a platform, from the buyer that would be attracted by the seller that you have just lost because you increased the fixed fee, right? And that is basically captured by these two terms here, right? So the fixed fee that you charge the buyers is negatively influenced by the utility of the buyer and the number of the buyers, right? So that's basically takes into account the network externalities of each market side. And the last term here, it's basically here with a plus, is how much does the number of buyers change, right? So it's basically a measure of sensitivity. And if the number of buyers is large, then this will increase the fixed fee. However, it is deflated by how much the buyers, that the number of buyers changes because if this one is large, so if the buyers are quite sensitive, then this decreases again your fixed fee for the buyers. And the same applies also to, if the number of buyers changes quite drastically, so if this term is large, then this will basically lead to a smaller fixed fee that you charge the sellers. Okay, now we can then come up with excess elasticities, right? So we can take what we had before and determine elasticities. In order to do that, I would advise you to take a look at the textbook here. So it's something that we don't derive here. However, what I want to show you is that you can use these definitions here to get to a learner index, right? So what you do is to just take these two fixed fees here and rearrange them so that you have on the left hand side fixed fee minus basically your cost over the fixed fee is 1 over the excess elasticity of the sellers, and the same of course for the buyers. And that's something that we have already encountered. It's basically a learner index. So recall that our learner index was the percentage markup over marginal cost, and we have derived in chapter, I think it was chapter A already, that the equilibrium markup, or that in equilibrium of a monopoly market, the learner index is 1 over the own price elasticity, right? And that's something that we have here as well, or something similar, right? And it's important to note that the markup that each market size can generate is decreased by positive externalities, right? Because you want to keep the markup, the market side on your platform that generates strong network externalities, right? So what you do is to decrease the fees that you charge on the market side that generates strong network externalities, because you want to have them on the platform because they attract the other market side. So if it is good for you to have a lot of buyers on the platform, so say a lot of players on an Xbox, you want to have the price for an Xbox relatively low, because that increase, or if the number of players make the platform attractive, developers for games want to develop games for the Xbox. If there are many people who use the Xbox, then you want to keep the price of the Xbox as low as possible, basically, in order to attract many buyers or many users, many players. And that could even lead to a situation where you subsidize one market size directly by charging them fixed fees that are below your cost of access, right? And that can happen if the externalities that are generated by that market size are small, right? Now, let us talk about what the monopoly effects are here. So we compare the monopoly situation to a social optimum. And the social optimum we can compute basically as the sum of our platform profits plus producer surplus. So what does the sellers earn on the platform, plus what do the buyers earn on the platform, so consumer surplus. And again, just keep in mind that the producer surplus is a function of Vs, and if we differentiate producer surplus with respect to Vs, we get to Ns, right? That's just something I would advise you to take a look at Belleflamme and Peitz here. It's easy to come up with that, but just let's have a look. And the crucial point here is if you take that into account and you differentiate your welfare function with respect to Vs, for instance, then you have this one, right? So is equal to the derivative of your profit of the platform with respect to Vs plus, and now the derivative of PS with respect to Vs is Ns, so you just add Ns, right? So recall that what we did a few minutes ago when we differentiated the platform profit function with respect to Vs. Now all you do is to look at the first order condition and add to the left hand side here Ns, right? And you see that this has a drastic effect or that has an effect on the surplus on each market side. So it will basically in equilibrium look something like this. If you solve that with respect to Vs and Vb and solve the system of equations, you get to this one. And if you then compute the equilibrium fixed fees on each market side, you get to these expressions here, right? And all you have to do at that point is to realize, or compare them with what we have here, right? So these were the fixed fees in monopoly, right? And you see here that this is the part that we also have in the social optimum, and this is the part that we only have in monopoly, right? So this term is positive, so what this means is that the fixed fee is higher in monopoly than it is in the social optimum, right? So something that is not very surprising, but if you want to interpret that, we just realize that this one is also present in the social optimum. However, this one is not. So what does it mean? Basically, we have from a welfare perspective the point that we also take into account the cost, which makes a lot of sense, and we also take into account the network externalities, right? But we do not take into account basically the excess sensitivities, and these excess sensitivities are basically something that are related to the quantity effects in the monopoly setting, right? So you just take into account that when you decrease or increase the fixed fee, you lose or attract, or depending on what you do, you lose or attract some parts of the respective market size, and that has a feedback on the other side, right? And that is something that, from a viewpoint of a maximizer here, does not happen. So we have this distortion goes away. Okay, now let us now talk about a situation where we have two platforms, right? What we do in order to analyze that is to assume that the number of buyers and sellers is equal to 1, which basically means that all the sellers go either to platform 1 or platform 2, and that is basically that the sum of the two is normalized to 100%, basically. Now, the surplus is the same as we had before, right? So for each seller that you have on the platform, the buyer realizes his utility U, and each buyer pays the fixed fee by accessing a given platform I, right? So the surplus that a buyer gets from visiting platform I or patronizing platform I is this term here, so the number of sellers on this platform times U minus the fixed fee that the buyer has to pay in order to access platform I. We assume that buyers are uniformly distributed on an interval 0, 1, so that's something that comes from the so-called hoteling model. I will explain you the basic ideas in a few seconds. I will just tell you that you could have a look at the I/O class that is also available on our channel, where Professor Götz digs into that topic a lot more deeper, right? So here we just do it rudimentary, basically. We assume that along this interval, the platforms are located on the endpoint, so I equals 1 is at 0 and I equals 2 is at 1. We assume full market coverage, so each consumer buys either from platform 1 or platform 2, but he does never not buy, basically. It's an assumption that has technically it makes life a lot easier, and if we drop it, it gets difficult, so we don't do that, because it doesn't really distort our message or our effects here a lot. So yeah, we assume that we have basically a linear transport cost, which is tau b and tau s for the respective market side. I will show you in a minute what that means, and we get these number of buyers and sellers here for each platform. This is something we will now we will want to understand in more detail. So how does this idea look like? We have here the line that we have just assumed, right? So there's a line from 0 to 1, and at 0 we have basically our platform 1. and at 1 we have our platform 2. Oh, sorry, 2. We have a seller. We take just one seller randomly, we pick him randomly, and we say that he's located here, right? So he has location theta. This theta is somewhere between 0 and 1, and in our example here, it looks like he would be located at 0.5, but it doesn't really matter to illustrate our concept. Now, what happens here? Suppose it is a seller, so it's a game developer, right? And suppose that platform 1 that is located to the left is the Xbox, and platform 2 that is located to the right is PlayStation. And the seller decides whether to develop a game for the Xbox or for the PlayStation. Now, the distance to each platform is measured by the location of the consumer minus the location of platform 1. Platform 1 is located at 0, so the distance from the seller's location to platform 1 is theta, and the distance from platform 2 is 1 minus theta, right? So that's basically the distance he has to travel to get to each platform. That's pretty abstract. What does this mean? Basically, it captures the idea of horizontal product differentiation. So that means that Xbox and PlayStation are not the same consoles, right? So sellers perceive them as different things. The original idea of that goes back to a paper of 1929 written by Harold Totelling, and he basically, I think he illustrated that as with a beach, and on each side of the beach, or at the endpoints of the beach, there are ice cream dealers, and depending on the proximity of a given consumer to a given ice cream dealer, the consumer patronizes either the ice cream dealer on the west side or the east side of the beach, basically. So that would be the idea. And the closer you are to the ice cream dealer, the more likely it is that you will, ceteris paribus, patronize the ice cream dealer. In the literal sense, this is horizontal product differentiation, and it captures the idea of geographic product differentiation. So you really physically have to walk to the ice cream dealer to buy your ice cream there. And the closer you are to the ice cream dealer, the more likely it is you will go there, right? So if you're sitting right next to the ice cream dealer, if prices are the same, pretty much unlikely that you go to the other ice cream dealer, right? And here, if we talk about game developers, the idea is pretty much the same, right? So if you, as a game developer, have always been developing games for a certain type of console, let's say you always develop Xbox games because your game fits the console very well, but it doesn't really fit the other console, then it would mean that you're closer to, in our example, you're closer to Xbox or you're closer to PlayStation, right? So I'm not an expert in this respect, but it could also mean that, for instance, if you have, if you talk about PC and a console here, it makes a lot of sense that if you have games where you have to press more buttons, then it's probably something that would be, the game is more likely to fit into a PC than it does into a console game, right? So usually for real-time strategy games, that's something that you usually develop for PCs because you have to press a lot of buttons, and that's something that you cannot easily translate into a console, right? So that would be an example here, right? Now let's get back to our abstract model here. What is the utility of the seller if he patronizes, if it patronizes platform 1 or platform 2? So if the game developer develops a game for Xbox or left platform here, then it would realize its utility that it gets from releasing a game on Xbox minus the traveling distance that it incurs in order to sell at Xbox. And that's the distance between its location and 0. 0 is where the Xbox is located, so that's basically tau times theta, right? So theta times 0, theta minus 0 times tau s. So this is the utility if the developer patronizes Xbox, and if the developer instead develops the game for PlayStation, then it gets net utility VS, sorry, gross utility V2S minus the traveling distance, which is 1 minus theta times tau S. Sorry, it should be the S and not the 5. Okay? Now, what do we do next? We want to determine the developer that is exactly indifferent between developing the game for Xbox and PlayStation. Why? Because we know that all developers to the left of this developer that is indifferent, all these developers will develop games for Xbox, and all the developers to the right will develop games for PlayStation. Why is that? Well, let us first derive what the indifferent consumer is. It's pretty easy. Right, so this is the utility that a given seller with location theta realizes when it develops a game for Xbox, or in other words, if he patronizes platform 1, and this is the utility for platform 2 vis-a-vis PlayStation. So all you do is to take these two equations and set them equal to one another, and then you rearrange the resulting expression with respect to theta, right? And you end up with theta times theta hat, and this is exactly this expression here, right? So this theta hat is the location of the seller that is indifferent between patronizing platform 1 or platform 2. In other words, this is the developer that is indifferent between developing a game for Xbox or for PlayStation. Why is that important? As I said, like, we go back to our illustration here. Suppose that this indifferent consumer would be exactly this one that we have analyzed here. Suppose this would be theta hat. Now we know that to the left of theta hat, all the thetas are lower than theta hat. So all those to the left of theta hat have a lower transport cost to patronize platform 1. So all the ones to the left of theta hat will go here. They will develop games for Xbox. And all the ones to the right, for them it is closer to develop games for PlayStation, right? So all the ones to the right of our indifferent consumer, indifferent seller, they will patronize platform 2, right? And based on that, we can determine our demand for the respective, or the number of sellers at the respective platform, and that is theta hat minus 0. So all the ones to the left of theta will develop games for Xbox. In other words, all the sellers to the left of the indifferent seller will patronize platform 1, and all the ones to the right, and this is down here, will patronize the platform 2, right? So theta minus 0, in other words, theta hat minus 0, theta hat are the ones who patronize platform 1, and 1 minus theta hat are the ones who patronize platform 2. Keep in mind here that we would usually have to take into account that this is a uniform distribution. However, we have normalized the interval here to be 0, 1, and we also have so we leave away any things regarding normalization here. So it makes life easier, right? Again, I would advise you to have a look at the IO course where we dig into that a little bit more deeper. Okay, now we just realize that we have normalized the number of on each side to be 1. So we have 100% buyers and sellers. That means that the number of buyers or sellers on a given platform is 100% minus, or 1 minus the number of buyers or sellers on the other platform, right? Now, if we substitute this information here into this one. And we rearrange this one with respect to, sorry, that isn't correct. That is not correct. Let me go back. So we take this information and substitute into here. Then we take this VIS and VIB and substitute into here. So that's Vj, so you just skip indices, you just flip indices, and you do the same here basically. And you then end up with this expression here. Right? And what does this expression tell you? Well, this is basically the number of sellers on platform I as a function of the buyers on the same platform, right? That's not our final result, so that's not something we need to compute something. It's just something that we want in order to understand what happens. Because you can see from here that if that one additional buyer attracts pi over tau s additional sellers, and VIV similarly for the buyers. How do we get that? Well, how does the number of sellers on a given platform change in the number of buyers on that platform? And that's exactly the information that we need. One infinitesimally small additional buyer on a platform attracts the derivative of that expression with respect to NIB, and that's exactly what we have here. So pi times 2 over 2 tau s, so 2 factors out and you have pi over tau s, and that's exactly the expression that we have here, right? And the same you can do for the sellers if you differentiate that one with respect to NIS. And it's important to note, although we won't dig into more detail here because it's quite technical, but the ratio between these two measures here, it measures the relative intensity of network effects. And if this ratio is too high, we only have one platform. Technically, if this ratio exceeds 1, we only have a monopoly. We have a monopoly platform. And if this ratio is smaller than 1, we can support 2 platforms in the market. Why is that? Well, it basically captures the tendency for monopolization in platform markets. Why is that? Well, we have just learned that network effects play a role here. That basically means, put to the extreme, that if all the buyers are on one platform, then it makes a lot of sense for all the sellers to also go to the platform. And if you just take one buyer away from that situation, it still makes sense for all the sellers to be on the platform, right? And basically, we have it's like a waterfall, right? So a critical mass. Once a critical mass of consumers or buyers or sellers is attracted to a given platform, all the others will come as well, right? You could think about that in a similar fashion as social media, right? So if you have a social media platform and once enough of your friends are on the platform, you will go there as well, right? That's the direct network effect. And if all persons in a given area are in one social media platform, it makes a lot of sense for advertisers to also be on that platform, right? Okay, so now it gets a little bit more tricky because if they're all the advertisers are one platform, it basically is costly for the buyers because you don't want to get a lot of advertising and things get a little difficult, but that's basically the idea here. Okay, now if we just substitute for NB here, or NS, vice versa, you get your number of sellers and buyers on a given platform only as functions of your fixed fees, right? And the same applies here. And Now we can analyze this in a little bit more detail, because we basically see that the number of sellers on a given platform, so NIS, increases when the fixed fee that is charged from the seller decreases. So if it gets cheaper for you to be on the platform because you pay less as a fixed fee, it's more likely that you are on the platform. And if the fixed fee that is charged on the other market side decreases. Why? And that's the indirect network effects. If it's more cheaper for the buyers to be on the platform, more buyers will be on the platform, and that will lead to more sellers being on the platform, right? Okay, so we can take this information, your NIS and your NIB, and set up the profit maximization problem here. And that is what we have done here. So that is our platform profits of a given platform I. And the platform I chooses its fixed fees for the buyers and the sellers optimally. And from each seller, it earns as margin the fixed fee for that seller minus the cost for serving the seller. And this is the number of sellers, right? So this is what we have here. And for the buyers, it looks exactly the same, right? So with the respective indices. Now, what you do is to differentiate this one with respect to MIS and MIB. You get two first order conditions that you can solve, and you can make life easier in this first order conditions if you assume that we analyze symmetric equilibria. And for that, in order to do that, we assume that the fixed fee that are charged to buyers are the same across the two platforms, and the same applies to the sellers. That does not mean that each buyer and each seller pays the same fee. It means that each buyer pays the same fee whether she goes to platform 1 or whether she patronizes platform 2, right? Okay, and if we do that, we will end up with this expression here, right? So how do the fixed fees look like in our platform competition example here? So they increase in cost, which makes sense. They increase in a measure of heterogeneity, so these are the transport costs, something I will address later. And they decrease in the degree of network effects. And that's also what we had in the monopoly example, because the same network effects are present, right? And this is basically this U over tau B tells you how many additional buyers are attracted by a seller. And here we have basically the profits that the platform realizes from this process, right? Again, taking into account the network effects. And we see that if these network effects are strong, this not only leads to, that basically means that competition between platforms is more fierce, because you see here, this is a minus, right? So this is basically the extent of network effects, the degree of network effects, and you see that here we have a minus, so the stronger the network effects, the lower your fixed fees, and that means in our competition example that basically you have fiercer competition between the platforms. So we would expect that if the degree of indirect network effect is strong, platform competition is more intense. Now, in expression 3, we have, again, ms as a function of mb. So all we have to do, again, is it's two equations and two unknowns, and we can solve that for ms and mb, and we will get to this term here. And that's pretty easy or straightforward to interpret. We see here that basically on a fixed fee on a given market side increase in basically the elasticity. So if a market side, just decrease that. That does not make sense. So if you have the fixed fee of a given market size, they decrease in indirect network effects. This is this part here, because you basically have to take into account that a seller attracts buyers, and that utility you get from the buyers, the stronger this is, and that this is basically takes into account the network effects, the more likely it is that you will have lower fixed fees. And the other thing is this tau s here. That's basically our parameter that measures differentiation. If tau s is high, then think back to our hoteling example. That means that it is very costly for you to take a given step on our hoteling line. In other words, it means that it's the market is, or the two variants here, the two platforms are pretty far away from one another. That means they are pretty differentiated, right? So if in a real world example where we don't talk about platforms, it would be you could be something like in one world where the degree of differentiation is probably not so high, you talk about like toast of one manufacturer versus toast of another brand, for instance, so like two brands of the same toast. However, if you have toast versus bread, the degree of differentiation is higher, right? And now that's basically measured by this tau s here, or the tau b, right? So it tells you how far the two platforms are perceived as substitutes. And if the platforms are perceived as homogeneous, that means that tau s is low, and then this would mean that the fixed fee are lower. And that's something that is quite in line with what we had in our competition models, for instance, in chapter G, where we have been talking about a differentiated Bertrand model, where we have assumed that if the degree of differentiation is low, the products are more homogeneous or perceived as more homogeneous, and prices will be lower, so price competition will be more fierce, right? And from there we can basically compute the equilibria, and you will see here that the profits also decrease in the degree of product differentiation. And yeah. Okay, now let us interpret our findings or talk a little bit more broadly about platforms, so going beyond our model. Now what we have not yet talked about is single and multi-homing. What is multi-homing? Recall that it means that agents can be active on multiple platforms at the same time, right? So it's quite easy for you to be on eBay and on another auction platform at the same time. It's easy for you to watch videos on YouTube and on TikTok or on other let's say social media platforms in a broader sense, right? So the market definition of social media is pretty difficult, but you get the idea, right? So if it's easier for you to be on multiple platforms at the same time, then you are a multi-homer, right? Or more likely to be a multi-homer. And the thing is that if there are single homers, then these are the ones that are not active on multiple platforms. What does this mean? Well, look, if it's difficult or expensive for you to have multiple gaming consoles, which is true in reality, then it's more likely that you only have one gaming console. And that would mean that you are basically a single homer, right? And it's basically the case that the platforms want to get the single homers on board, right? Ceteris paribus. Of course, it also depends on their degree of network effects, but ceteris paribus, it's more likely that the platform wants to attract the single homers because the multi-homers will be on their platform anyway, right? So they have low cost of accessing the platform. That means that multi-homers will pay a little bit more, ceteris paribus, than single homers. And again, it might even be the case that the fixed fees that are charged from the single homers are lower than marginal cost. Another thing is that network effects can be so strong that they tend to monopolize the market, right? So again, I've told you the example that if there is a platform and the network effects are very strong, then it's probably efficient, or yeah, with efficiency we have to be careful, but it might be very, very likely that all consumers and all sellers and all market participants are on the same platform, because that maximizes the degree of indirect network effects. And I have to refer to the Digital Markets Act here that was introduced by the European Union, and that exactly basically takes into account this effect and proposes a more offensive how do we say that? They basically propose to be more offensive regarding that platform suppliers when this taking into account this tendency of monopolization, because it can have negative consequences, of course. And the point is that if we talk about, or if we analyze this cross-subsidization aspect, then we are reminded of multi-product firms, right? So it's for some products you price below marginal cost, for some products you price probably above marginal cost. So we have some things that are quite attractive for the consumers, and that is basically what you want to sell fiercely. However, there might be other products that are probably have to be sold cheaply because that attracts other consumers, for instance. And the same applies, the same concept applies to network effects. And it's also important to take into account that if the network effects are very strong, it might even be optimal from a welfare perspective to have a single platform. Why? Because basically you internalize the network effects, the externalities, in an efficient way. And if we talk about the SNP test that we have been analyzing in our course, the small but significant non-transitory and price test, that is difficult to apply to two-sided markets. So recall what the test was. It basically means that we assume that there's a hypothetical monopolist, and that hypothetical monopolist increases prices by, we said, 5 to 10%, right? However, we have two prices here. We have per unit fees and fixed fees, and it's not so trivial, as both prices have a distinct function in our two-sided market example. So how do we assess that in our SNP test? And it's also that these prices are not charged only to a single side, they are charged on both sides. So we basically have 4 prices here. And it's also important to take into account that when we do that SNP test, there are indirect network externalities. So probably a monopolist, even if it's a monopolist, then it will have fixed fees very low for one market side, so that increasing prices on that market side doesn't make sense, because he loses because the monopolist loses too many participants on the other market side due to the strong network externalities. So it will be ideal for a monopolist to set low fixed fees, and increasing those fixed fees will not be profitable by definition, right? And that's something that does not work with our traditional, it's not in line with our traditional SNP idea. And that brings us to the general debate on market power in two-sided markets here, right? So if you do a cost-based analysis on the price structure, that does not make sense at all, right? Because we have that type of network externalities that are taken into account, right? And if we have prices below marginal cost, that does not mean that we have predation. That means that we want to drive out other platforms from the market, because this is basically just the measure to attract, for instance, the single homers or the market side that exerts a strong network externalities on the other market side. And it's also the case that competition between platforms is not necessarily what we want from an efficiency perspective, because of the network externalities, right? So it's probably efficient to have one platform where all the buyers and all the sellers are, because they have the strongest, that generates the strongest externalities. A problem, though, is exclusivity clauses that we have addressed in chapter H3, because that's something that is quite present in these two-sided markets. So there are currently some proceedings not only in Europe but also in the US that basically attack exactly this, because they say that a given platform binds its users to exclusively use that given platform and not consult another platform. Right? So that is something that is really, really important in our current competition policy debate. Now, finally, we talk about collusion. if we want platforms to collude, well, we don't want them to, but if there would be, if we analyzed platform collusion, then the thing would be really difficult, because in general, collusion on platforms is less stable, because if you not only have to take into account deviation on one market side, but also deviation on the other market side. So it might be pretty difficult to maintain that. And the other thing is that collusion can even enhance welfare if the network effects are internalized more efficiently, right? So we might actually collude in order to set efficient pricing schemes. And that is, I would just advise you to take a look at the Nabanco Visa case in that case. Okay, so we have now been talking about, or we have talked about everything that I would like to address with respect to two-sided markets. It's a very, very, very broad topic nowadays, not only with respect to theory, but also empirical research and you know, the competition policy behind it. And that's just something that it goes far beyond the purpose of our introductory course here. So it would really make sense to have a dedicated course for that. However, that's something that is probably, it's something for another topic, basically. So, for today, I would like to thank you for your attention. We would be very happy if you could like the video and subscribe to our channel, and we would appreciate having you using the comment section. So if you have questions, please just post them in the comment section below. Thank you, and see you in the next one.